Good morning, dear students. Today we are going to discuss about Biot Savart's law. Already in the previous section, you studied about Ayerstedt experiment where a current carrying conductor is surrounded by magnetic fields. If a current carrying conductor is surrounded by magnetic field or produces magnetic field, then what will be the magnitude of the magnetic field and what will be the direction of the magnetic field at any point around the current carrying conductor? That was determined by Biot Savart's law. Biot and Savart, Jean-Baptiste Biot and Felix Savart in 1819, they studied the force acting on a magnet placed close to a current carrying conductor, and it experienced a force. They measured the force on a current carrying force on the magnet, and then they determined the expression for the magnetic induction at any particular point due to this current carrying conductor in terms of the current flowing through the conductor. If a conductor is carrying current, if we want to calculate the magnetic field at the point P, then the magnetic field at the point P is expressed in terms of this current I. And this is applicable and this is true for conductors of any shape. This is true for conductors of any shape. Now we can bring out the expression which was already given out by Biot Savart. We can show here, when a current carrying conductor is connected to a source of potential difference V, let us say XY be the current carrying conductor. This is connected to a source of potential difference V. Then it carries the current I. This current I flows through the conductor XY, and in this conductor I am assuming a small element, let us say dl, and a point P is considered where the value of magnetic field has to be determined, dB has to be determined. I can represent it in terms of vector. This point P is at a distance r from this current element dl. What is this current element called? We are going to calculate the magnetic induction at the point P due to a small segment of the entire length of the conductor. So procedure is very simple. We are going to blend the mathematical idea, integration, here in determining the value of magnetic induction at the point P. So in order to determine the magnetic induction at the point P due to the entire length of the conductor, the very first thing what we are doing is, we are going to calculate the magnetic induction at the point P due to the small element dl. Then you are going to divide the entire length of the conductor into so many number of such small elements. If all the magnetic inductions are added up on the basis of principle of superposition, then you will get the total magnetic induction at the point P. dl is a very small segment of the conductor, infinitesimally small segment of the conductor. If I represent this as delta L, that refers to a measurable amount of length. If I represent it as dl, that is the infinitesimally small segment of the entire length of the conductor. I have divided this entire length of the conductor xy into so many number of such small elements dl. Each and every element will produce its own magnetic field at the point P. If this dl produces the magnetic induction dB, then all the elements will produce the same amount of magnetic induction if the elements are of equal lengths. If the elements are of equal lengths, then the magnetic inductions produced at the point P will also have the same magnitude. If you add up all the magnetic inductions at the point P, then you will get total magnetic induction at the point P due to the entire length of the conductor. So, what exactly you are doing is, if you simply add up all the small elements, if it is given in terms of intervals, then we have to go for summation. If we add all the small elements, infinitesimally small elements dl, then we are going for integration. So if you integrate with the proper limits between these two conductors x and y, which encloses all the small elements, then you will determine the magnetic induction at the point P. So quantitatively, they arrived at an expression based on their experiments that the magnitude of magnetic field dB. See, if I represent simply dB, it refers to magnitude. If I represent it as dB vector, then it has both magnitude and the direction. Magnetic induction is a vector quantity, so it has both magnitude and the direction. The magnitude of magnetic induction dB is directly proportional to the current I flowing through the conductor. It is directly proportional to the elemental length dl of the conductor. See, it depends upon, dB depends upon the current flowing through the conductor. Also the dB depends upon the elemental length dl of the conductor. And also it depends upon sine of the angle theta. This is angle theta, which is marked between the current element and the position vector. Current element and position vector. So dB is directly proportional to sine of the angle theta between the current element and the position vector r cap. And then it is inversely proportional to square of the distance between the current element and the point P. Square of the distance between current element and the point P. What is the distance between current element and the point P? R. So inversely proportional to R square. So we can conclude that this magnetic induction dB is inversely proportional to R square. In turn, we can say it obeys inverse square law. So Biot-Savart's law is in the form of inverse square law. So as a cumulative expression, I can write dB is proportional to I, directly proportional to I, directly proportional to dl, directly proportional to sine of the angle theta, and inversely proportional to square of the distance between the current element and the point P. So if I cancel the proportionality, I can write a constant k. dB equals k I into dl sine of theta divided by r square. And this constant can be replaced with some numerical value. I can write this value of k is mu naught divided by 4 pi in terms of SI units, and this is equal to 1 in terms of CGS units. So if I am expressing this value of magnitude in terms of SI units, then I have to use the constant as mu naught by 4 pi. In terms of CGS units, I have to use the value of constant k as 1. We are always discussing the fundamentals in terms of SI units. So I can write dB is equal to mu naught divided by 4 pi. This is mu suffix o. Mu naught divided by 4 pi, where mu naught is the permeability of free space or vacuum, which is 4 pi into 10 power minus 7 Henry per meter. Mu naught by 4 pi ideal sine of theta divided by r square. This can be expressed in terms of vector notation. In vector form, I can represent dB vector is equal to mu naught divided by 4 pi I into dl vector cross r cap divided by r square. See this one? Ideal sine theta. So I am bringing out a unit vector here, r cap. So if I am taking a product with the unit vector, simply I can represent it. See, dB equals mu naught by 4 pi ideal sine theta divided by r square gives you the magnitude. If I want to convert this magnitude in terms of direction, I have to multiply it with the unit vector. Then this will become a vector. This entire magnitude exists as it is. If I am multiplying it with the unit vector, then this quantity will become a vector. So dB vector equals mu naught by 4 pi ideal sine theta by r square into r cap. In vector cross product, because we are having a vector, b vector, sine of theta. So dB vector equals mu naught by 4 pi ideal vector cross r cap divided by r square. This is also expressed in another form. Mu naught divided by 4 pi ideal vector as it is. If I convert this unit vector, vector divided by its own magnitude, so I can write r vector divided by, already an r square is existing, so this will become r cube. So dB vector equals mu naught by 4 pi ideal vector cross r cap divided by r square, or mu naught by 4 pi into ideal vector cross r vector divided by R cube. This is the expression for magnetic induction at the point P due to the small elemental length dl. But what is our intention? We have to find out the total magnetic induction at the point P due to the entire length of the conductor xy. In order to determine the total magnetic induction, as I mentioned you earlier, we have to undergo or you have to carry out superposition principle or principle of superposition. What is that? Each and every element will produce the magnetic induction at the point B. You have to sum up all the elements by taking proper limits between these ends of the conductor xy. So that will include all the current elements. Also, that will bring out all the magnetic inductions produced at the point P in a summed up form. So total magnetic induction will be obtained. What is the direction of this dB vector? In what direction this dB vector will act? We can simply say, we have taken a cross product here, ideal vector cross R vector, R cap. So, I can say, ideal vector is in this direction, R cap is in this direction. These two are lying in this plane, in the plane of board. Then dB vector will act perpendicular to the plane of the board. If I mark a cross with a circle, then this denotes inward action of fields. If I mark a dot with a circle, then it represents outward action of the fields, whatever the field is. We are speaking about the magnetic field. So a cross with a circle represents the inward action of magnetic field at the point P. So the magnetic field will act perpendicular to the plane of the board, inwards, perpendicular to the plane containing ideal vector and R vector. Ideal vector is there, R vector is here, these two are lying in the same plane. As you know, if you apply right hand rule in vector cross product, then we can simply say ideal vector is along this direction. I can mark this. Ideal vector is along this direction. R vector is along this direction. Theta is this angle. I have to go through the smallest angle. So ideal vector cross R vector. If I rotate it, the thumb is projecting inwards. So thumb gives you the direction of the third vector. So dB vector is the third vector, will be acting perpendicular to the plane of the board, inwards. In order to represent it clearly, in order to picturize it clearly, I am representing a cross with a circle. So this is dB vector. So you rotate ideal vector towards R vector where the thumb is projecting. Thumb is pointing inwards. So thumb gives you the direction of the magnetic induction at the point P. That is inward. So total magnetic induction can be determined by integrating this entire quantity, this magnitude, with proper limits. Here I am just giving out a general expression that integral of dB is simply b. This is equal to integral of mu naught I divided by 4 pi a, mu naught I by 4 pi r, mu naught I by 4 pi r square, I into this dl sin theta into n cap. These are all different expressions. Mu naught I by 4 pi r square dl sin theta into n cap. I can take out this mu naught divided by 4 pi and I can express this as ideal vector cross r cap divided by r square. I can represent r cap or n cap unit vectors. So this will give you the magnitude, means the total magnetic induction at the point P. B vector is equal to mu naught by 4 pi into integral of ideal vector cross r cap divided by r square. So this is the expression for the Biot Savart's law. This will give you the total magnetic induction. This will give you the magnetic induction due to a small element. This is due to a small element. This is due to the entire length of the conductor. We can determine magnetic fields due to any type of conductor. This is true for all the conductors with the different shapes. Fine. What are the similarities between this Biot Savart's law and the Coulomb's law, which you studied earlier? Can speak about similarities. Similarities. This is Coulomb's law is for electric field and Biot Savart's law is for magnetic field. Both obey inverse square law. Both obey inverse square law. Both obey inverse square law. Both Biot Savart. This is Coulomb's law. This is Biot Savart's law. We are speaking about the similarities. Coulomb's law deals with the electric fields, and Biot-Savart's law deals with the magnetic fields due to current carrying conductors. Both the laws obeys inverse square law. So we can say these electric and magnetic fields are long range fields. Long range fields because they vary with the distance, they depend upon distance. So they are long range fields. And then they obey principle of superposition. They obey principle of superposition. Also, their magnitudes are linear in magnitude. We can say here, they are linear in magnitude. They are linear in the sense electric field depends upon charge and magnetic field depends upon the current element. So they are linear. So in magnitude, I can represent E is directly proportional to Q and B is directly proportional to IDL. So in magnitude, electric field depends upon charge and magnetic field depends upon current element. This is about the similarities of the Coulomb's law and Biot-Savart's law. Coulomb's law deals with the electric field, Biot-Savart's law deals with the magnetic field. As you know very well, in Coulomb's law also we speak about inverse squares, law of inverse squares. In Biot-Savart's law also we are speaking about law of inverse squares. So they obey inverse square law. So we can conclude that the Coulomb's law and the Biot-Savart's law, which are bringing out the electric and magnetic fields, are long range fields. They obey principle of superposition. Also, the fields are linear with their respective sources. The fields are linear with respective sources. In magnitude, we can represent E proportional to Q and B proportional to ideal. So, to conclude, already in our study experiment, we studied that there is an existence of magnetic field around the current carrying conductor. Fine. What will be the magnitude of the magnetic field at different points from a current carrying conductor? What will be its direction? That was determined by Biot-Savart's law. That was studied by Biot-Savart's law. This is a quantitative expression. So, the magnitude of magnetic induction due to a small element dl of a current carrying conductor carrying current I is directly proportional to the current I, directly proportional to the current element dl, directly proportional to sine of the angle theta between current element and the distance between the current element and the point, and is inversely proportional to square of the distance between the current element and the point. And summing up, dB proportional to ideal sine theta by r square, introducing a constant by cancelling the proportionality, dB equals k ideal sine theta by r square. Constant k is expressed in terms of mu naught by 4 pi when we use SI units and is equal to 1 in CGS system of units. We use SI system of units. So dB vector equals mu naught by 4 pi ideal sine theta by r square into r cap. If I multiply this magnitude with r cap, then this will become a vector. So magnitude is simply dB equals mu naught by 4 pi ideal sine theta by r square. In vector form, this dB vector can be given in terms of cross product, mu naught by 4 pi ideal vector cross r cap divided by r square. With this cross product, by applying right hand rule, I can say the direction of magnetic induction dB vector will act perpendicular to the plane containing the two vectors ideal vector and r vector. And this is also expressed in terms of mu naught by 4 pi ideal vector cross r vector divided by r cube. See this one, when you express in terms of unit vector, denominator will be possessing a power r square. In terms of vector, it will be r cube. So total magnetic induction at the point P due to the entire length of the current carrying conductor is obtained by using principle of superposition. You have to integrate. So integral of dB vector is equal to B vector, which is equal to integral of mu naught I by 4 pi r square dl sin theta into r cap. This B vector equals mu naught by 4 pi integral ideal vector cross r cap divided by r square. Then similarities between Coulomb's law and Biot-Savart's law. Coulomb's law is for electrostatics, Biot-Savart's law is for magnetostatics. Deals with the electric field, that one is dealing with magnetic field. Both obey inverse square law, so the fields are long range fields. Both obey principle of superposition. Also, the respective fields are linear with the respective sources, and in magnitude that can be expressed as E proportional to Q and B proportional to ideal. Note in this equation or in this expression, I am writing E proportional to Q and B proportional to ideal. The exponents of E and exponent of q are unity in this expression. So what is exponent here? Exponent is nothing but power of a given base. So if I write the expression E proportional to Q, the power of E and Q is 1. Similarly, B proportional to ideal, the powers are 1. So the exponent of electric field and exponent of the charge are unity. The exponent of magnetic induction and exponent of current element are also unity. So we can simply say, or what does this mean? We can simply say here, E is not dependent upon the powers of the charges like q square, q cube, etc. Similarly, B is not dependent upon ideal square or ideal cube, etc. So they are not dependent upon their higher powers. Simply they are dependent upon the respective sources like E proportional to Q and B proportional to ideal. Then what does this mean? E varies linearly with Q and B varies linearly with ideal. So their respective fields are linear with their respective sources. Charge E proportional to charge and B proportional to the current element. Fine. We shall now speak about the difference between the Coulomb's law and Biot-Savart's law. What are the differences between Coulomb's law and Biot-Savart's law? You can write here. Difference between Coulomb's law and Biot-Savart's law. Difference between Coulomb's law and Biot-Savart's law. In Coulomb's law, the electric field depends upon a scalar quantity, let us say charge. In Biot-Savart's law, the magnetic field depends upon the current element ideal, which is a vector quantity. Charge is a scalar quantity. So E depends upon charge, which is a scalar. Magnetic induction depends upon a vector quantity, which is ideal vector. And second thing, the direction of electric field is E vector. E acts along the position vector R vector, which is connecting the source charge Q and the point P. If charge Q is here, point P is here, and then the electric field will act along the same direction as that of the position vector. Electric field will act along the same direction as that of position vector. I am taking a charge plus Q. The field due to the charge plus Q will act along the direction of position vector. Whereas magnetic induction, the direction of magnetic field is perpendicular to the plane containing ideal vector and R vector. So it is perpendicular to the position vector. In terms of position vector, I can say B vector acts perpendicular to position vector because it depends upon a vector quantity, ideal vector, which is nothing but the current element. So B is perpendicular to ideal vector and R vector, whereas E is acting along the direction of position vector. Electric field depends upon angle theta. That means it is independent of angle theta. Sorry, independent of theta. There is no such term theta existing in the determination of electric field. Whereas in Biot-Savart's law, the magnetic induction depends upon the value of theta, angle between the current element and the position vector. So we can say here the difference between Coulomb's law and Biot-Savart's law is very simple. Electric field depends upon a scalar quantity, let us say charge, and magnetic induction depends upon the current element, which is nothing but a vector quantity. Electric field acts along the position vector, which is the line which connects the line or which connects the charge and the point where the electric field has to be determined. So field acts along the direction of position vector. B vector, magnetic induction is perpendicular to ideal vector and R vector. So magnetic induction acts perpendicular to the vectors, ideal vector and R vector. Position in terms of position vector, it acts perpendicular to it. And then the electric field is independent of theta. There is no such angle existing. Whereas in Biot-Savart's law, it depends upon the value of theta between the current element and the line joining the current element and the point. Or otherwise, in terms of position vector, I can simply say it depends upon the angle theta between current element and the position vector. Now, we are going to speak about the application of a Biot-Savart's law. We are going to determine the magnetic induction due to an infinitely long straight conductor carrying current. Let us consider Nm be a long straight conductor, infinitely long straight conductor carrying current. Infinitely long. What does this mean? Infinitely long straight conductor. Shall we say the ends cannot be seen? No, I have marked the ends as N and M. So this is an infinitely long straight conductor. When compared to the dimension, the thickness of the wire must be very, very small. The area of cross section of the wire must be very, very small. So that the length, even in terms of 1 meter, is supposed to be infinitely long. Infinitely long here refers to the dimensions. If the length of the conductor is much larger when compared to the thickness of the wire, current carrying conductor, then the wire is supposed to be an infinitely long straight conductor. Nm be the conductor carrying current. Let us say I be the current flowing through the current carrying conductor. O be the midpoint of the current carrying conductor. I am considering a point P where the magnetic field has to be determined. I have to determine the value of magnetic field. This is at a distance A from O. The point P is at a distance A from O of the current carrying conductor. I am assuming a small element, let us say dl. This is at a distance L from the point O of the conductor carrying current. So the current element dl is at a distance L from O. We have to calculate the magnetic induction at the point P due to the small element dl. Due to the small element dl. Let us mark the position vector as r vector here. So r vector is the distance or position vector which connects dl vector and the point P. Let us say theta be the angle made by the position vector with respect to the current element dl. So if current itself is a scalar, if current is taken in terms of a small element dl, through a small element dl, then it is said to be a vector, ideal vector. I is a scalar. So dl is the small element. You are connecting the point P. We can say that r is the position vector which connects this current element and the point P. Theta is the angle between the current element and the point P. We have to determine the magnetic induction at the point P due to the small element. And then as per principle of superposition, we have to go on with the integration. Let us say phi1 be the angle made here at the end N of the conductor, and phi2 be the angle made at the end M of the conductor. Then I have to determine the magnetic induction between these two ends M and N at the point P. So we are considering this. The magnitude of everything is represented here. The magnitude of magnetic field as per Biot Savart's law is dB. Then with direction I can represent it as dB vector. This is expressed as mu naught by 4 pi I dl sin theta divided by r square into n cap, or otherwise I can say a unit vector perpendicular to ideal vector and r vector. I can say this unit vector as n cap. I am taking it as n cap. So dB vector equals mu naught by 4 pi ideal sin theta divided by r square into n cap. This will give you the magnitude and direction of the magnetic field at the point P due to the small element dl. Now to determine the total magnetic induction B at the point P, we have to take integration between the ends N and M with the limits phi1 and phi2. Then you will get total magnetic induction at the point P. Before doing that, we have to convert this expression in terms of some known quantities. So we have to do some manipulations here. If this is theta, total angle is pi, and this angle must be pi minus of theta. This angle is pi minus of theta. This is 90 degree, as you know. Right. I can say tan of pi minus theta is minus tan theta, which is opposite side divided by adjacent side. Opposite side is A, adjacent side is L. So minus of tan theta equals A divided by L. This is taken in the triangle OP. Let us mark this as A. In triangle OPA, we can say tan of pi minus theta equals minus tan theta, which is equal to A divided by L, from which L can be calculated. L equals A by minus of tan theta. This is minus of A cot theta, since 1 by tan theta equals cot theta 1. Then if I take sine of pi minus theta, this is sine theta itself. Sine theta equals opposite side divided by hypotenuse from the same triangle, which is A divided by R. So R equals A divided by sine theta. This is equal to A cosecant theta, since 1 by sine theta equals cosecant theta. So R equals A cosecant theta, L equals minus of A cot theta. I am going to differentiate this L with respect to theta. So dl divided by d theta equals d by d theta of minus of A cot theta. This is equal to minus of minus plus A cosecant square theta, since differential of cot theta is minus of cosecant square theta, minus of cosecant square theta. So minus into minus will become plus A cosecant square theta. So what is dl then? A cosecant square theta into d theta. Let us mark this as 3. Now we obtained the value of dl. We got the value for L from which we are determining the value of dl. We also had the value of R. By substituting all these values in this expression, I will get a different form of dB here. So dB vector is equal to mu naught divided by 4 pi I into dl is A cosecant square theta d theta divided by R is A cosecant theta, R square is A cosecant theta the whole square into sin theta into n cap. This is the position unit vector. So n cap, sin theta into n cap. So I can write mu naught divided by 4 pi I A cosecant square theta d theta divided by A square cosecant square theta into sin theta into n cap. Cosecant square goes off, A cancels out. I will have mu naught I divided by 4 pi A into sin theta d theta n cap. This is dB vector. So we got an expression for the magnetic induction at the point P due to a small element dl. Due to a small element dl, which is dB vector. This is equal to mu naught I by 4 pi A sin theta into d theta into n cap. Note, we expressed the magnetic field in terms of angular coordinate theta. We expressed the value of magnetic induction in terms of angular coordinates theta. In order to determine the total magnetic induction B at the point P, we have to undergo an integration between the limits of theta as phi 1 and theta ending with phi 2. So we have to integrate between the limits phi 1 and phi 2. If this expression is integrated if this expression is integrated between the limits phi 1 and phi 2, you will get total magnetic induction at the point P due to the entire length of the current carrying conductor. So, can go on with the integration. Integral of dB vector is equal to B vector itself is equal to integral between the limits phi 1 to phi 2 mu naught I divided by 4 pi A into sin theta d theta n cap. Constants are taken out, mu naught I by 4 pi A is taken out, integral phi 1 to phi 2 sin theta d theta into n cap. This is equal to B vector. What is integral of sin theta? Integral sin theta equals minus of sin theta d theta is minus cos theta. Sin theta d theta is minus cos theta. So I can write B vector is equal to mu naught I divided by 4 pi a into minus of cos theta between the limits phi 1 to phi 2 into n cap. If I apply the limits, upper limit minus lower limit, I will have mu naught I by 4 pi a, minus is taken out, cos of phi 2 minus of cos phi 1 into n cap. And taking negative sign into the bracket, you will have mu naught I divided by 4 pi a into minus cos phi 2 plus cos phi 1 into n cap. Or else you can write mu naught I divided by 4 pi a into cos phi 1 minus of cos phi 2 into n cap. This is the expression, this is the general expression for magnetic induction at any point due to a current carrying conductor, infinitely long state conductor carrying current. B vector equals mu naught I by 4 pi a into cos phi 1 minus of cos phi 2 into n cap. Actually, this is for the segment. If I consider this as an infinitely long state conductor, what will happen if this conductor is supposed to be infinitely long state conductor? Then what will happen? The point P connecting these ends M and N will be like this. It will come closer to this current carrying conductor. Almost it will become parallel. Almost it will come parallel. So what will happen? This value of phi 2 will be approaching towards 180 degree, and this value of phi 1 will be approaching towards 0. So if I say it is an infinitely long state conductor, then this point will be very, very close to this conductor, since this length of the conductor is infinitely long. So what will happen? This conductor is infinitely long. This point P is here. Then what will happen? This theta, see this one, this theta or this angle phi 2 becomes 180, and this angle phi 1 goes to 0. So for infinitely long state conductor, this expression is for the finite length of a conductor. This expression is for a finite length of the conductor. For infinitely long state conductor, phi 1 goes to 0 and phi 2 becomes 180. So B vector is equal to mu naught I divided by 4 pi a into cos 0 minus of cos 180 into n cap. Cos 0 is 1, cos 180 is minus 1. So 1 minus of minus 1 is plus 1. So 2 mu naught I by 4 pi a into 2 into n cap. This is B vector. This 2 cancels out. So B vector, I am writing the result here. B vector equals mu naught I divided by 2 pi a into n cap. This is the magnetic induction at the point P due to infinitely long straight conductor carrying current. And the n cap is the unit vector acting perpendicular to the plane containing ideal vector and r vector. So n cap here is the unit vector acting perpendicular to the plane containing ideal vector and r vector. So this is the expression, or this gives you the expression for the Biot Savart's law due to a long state conductor or infinitely long state conductors. Idea is very simple, that final results are very important in solving problems related to Biot Savart's law. There are a number of problems given to solve. So once again I would like to explain that whenever you are writing a description, you must be very familiar and clear with the diagram. Let us say NMB, the current carrying conductor carrying current I. You are assuming a point P at a distance A from O. Then you are assuming a small element dl in the current carrying conductor, which is at a length L from O. We have to determine the magnetic induction at the point P due to the small element dl. So the element and the point P is connected by a position vector, let us say r vector. So distance is taken to be r. Theta is the angle made between the current element and the position vector. The angles made at the point n is pi1 and m is pi2. Now, the magnetic induction at the point P due to the small element dl by Biot Savart's law is dB vector equals mu naught by 4 pi ideal sin theta by r square. As I am representing it in terms of vector, I need a unit vector here. So a unit vector must be perpendicular to the plane containing ideal vector and r vector. I am considering it as n cap. So unit vector is taken. Now, in order to calculate the total magnetic induction at the point P due to the entire length of the current carrying conductor, we have to undergo integration between the limits which are enclosing all the small elements existing between these two ends, m and n. So, simple. Actually, as I mentioned earlier, that is based on superposition principle. In order to do that, I am going to convert this entire expression in terms of some known quantities. So in the triangle OPE, tan phi minus theta, actually you can just go through it, minus tan theta, which is a by l, from which l is calculated as minus a cot theta. Sin pi minus theta is sin theta, which is equal to a by r is a cosecant theta. dl are in differentiating l with respect to theta. So dl by d theta is d by d theta of minus a cot theta, which is a cosecant square theta, because d by dt of d theta of cot theta is minus of cosecant square theta. d by d theta of cot theta is minus cosecant square theta. So dl is a cosecant square theta d theta. I am substituting for dl and r. So the expression becomes dB vector equals mu naught by 4 pi I a cosecant square theta d theta by a cosecant theta square sin theta into n cap. On cancelling and simplifying, you will have dB vector equals mu naught I by 4 pi a sin theta d theta into n cap. This is for the magnetic induction due to a small element dl. What is the total magnetic induction for the entire length of the conductor? We have to, if you look at this expression, we have expressed the value of magnetic field in terms of angular coordinates, which is theta. So we have to integrate this entire length of the conductor in terms of these angular coordinates, as theta equals phi1 and theta equals phi2. Phi1 and phi2 are the limits which encloses all the elements existing between the ends of the current carrying conductor. So integral of dB vector is b vector, which is equal to integral phi1 to phi2 mu naught I by 4 pi a sin theta d theta n cap. Constant is taken out. Integral of sin theta d theta is minus cos theta, and I am applying the limits phi1 and phi2. So here is that. On substituting the limits, minus is taken out here, cos of phi2 minus cos phi1, minus is introduced, minus cos phi2 plus cos phi1. So this conversion is important. You have to carefully go through it. B vector equals mu naught I by 4 pi a cos phi1 minus cos phi2 into n cap. This is for finite length of the conductor. I can say this is for finite length of the conductor. Don't forget. For finite length of the conductors, the determination of magnetic field is given by B vector equals mu naught I by 4 pi a into cos phi1 minus cos phi2 into n cap in the form of vectors. For infinitely long straight conductors, angle phi1 becomes 0, angle phi2 becomes 180 degree. So B vector equals mu naught I by 4 pi a cos 0 minus of cos 180 into n cap, which is 2. 2 and 2 gets cancelled here, remaining 2 is there. B vector equals mu naught I by 2 pi a into n cap. This expression gives you the total magnetic induction due to infinitely long straight conductor carrying current. You have to look at the question, whether it is infinitely long or finitely long. Infinitely long, that is the expression. Finitely long, this one is the expression. N cap, as you know, it is the unit vector acting perpendicular to the plane containing ideal vector and r vector. As I told you, y phi1 equals 0 and phi2 equals 180 degree when you carry out when you consider it for infinitely long straight conductor. Idea is simple. As you go infinitely long, then this point is considered to be very close to the current carrying conductor. If it comes close to the conductor, then the angle phi1 is like this. As you go close to it, when it is infinitely long, then this will come parallel. So phi1 will become 0 and phi2 will become 180 degree. So substituting the limits, you will get the field due to infinitely long straight conductor carrying current. Thank you.